The next topic in bonding will be the Localized Electron Bonding Model. The first part of the Localized Electron Bonding Model is coming up with good Lewis dot structures. And as we go through Lewis dot structures, we'll see most molecules obey the Octet rule, but we'll see there are several exceptions to this rule. The Localized Electron Bonding Model says that a molecule is composed of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of the bound atoms. Here, electron pairs are assumed to be localized on a particular atom or in the space between two atoms. Lone pairs are pairs of electrons localized on a single atom. Bonding pairs are pairs of electrons found in the space between the atoms. So keep in mind this localized electron bonding model is a model. As any other model, it's the best explanation that we can give. And this applies to covalent bonds. As we go through the localized electron bonding model, we'll be looking first at the description of valence electron arrangements and coming up with Lewis structures. Then we'll be trying to predict geometries of molecules using the valence shell electron pair repulsion model in another section. And then we'll be going through the description of atomic orbitals and the types used by atoms to share electrons or hold lone pairs in Chapter 9. Now, Lewis structures show how valence electrons are arranged among atoms in a molecule. This reflects the central idea that stability of a compound relates to noble gas electron configuration. Again, most of our elements will share electrons so that they can attain a noble gas electron configuration of 8 electrons. We'll see that hydrogen forms stable molecules where it shares only 2 electrons. We know that hydrogen is one of our diatomics. Each of the hydrogen atoms shares 1 electron. That even sharing of 2 electrons between our hydrogen atoms is a covalent bond, and we have a duet of electrons. Remember, hydrogen is in the first period of the periodic table. It only has a 1s orbital to fill. Once its 1s orbital is filled, it has a filled subshell. Filled subshells are the configuration of noble gases. The noble gas configuration that hydrogen attains through covalent bonding is the same as helium, also in the first period of the periodic table. So hydrogen forms duets. Similarly, lithium and beryllium lose electrons to form ions. They're metals and have this 1s2 electron configuration for their atoms. But here we're focusing on covalent bonding. That shared pair of electrons between 2 atoms can be shown by a dashed line between the 2 atoms. Now let's look at fluorine. Fluorine has 7 valence electrons. It is a halogen. All halogens have 7 valence electrons. Fluorine is also a diatomic. Each of the fluorine atoms shares 1 electron with the other fluorine atom. This is a purely covalent interaction because fluorine and fluorine are the same. By sharing that one electron, each of the fluorine atoms will gain an octet of electrons. All halogens will form a duet, will form a diatomic as fluorine does and gain an octet of electrons. Now, we don't only have to have single bonds between atoms. We can have double bonds where a covalent bond is sharing two pairs of electrons between two atoms. Here, the central carbon atom is sharing two pairs of electrons with the oxygen on the right. It's also sharing two pairs of electrons with the oxygen on the left. Through those covalent interactions, the central carbon has an octet of electrons. If we count the shared electrons plus the lone pair electrons on each oxygen, we'll get an octet of electrons on each oxygen. We can also form triple bonds, where we have a covalent bond in which two atoms share three pairs of electrons. In the diatomic nitrogen, N2, we have 6 electrons shared between the nitrogens and a lone pair of electrons on each nitrogen to give us an octet of electrons on each nitrogen. So let's go through some steps for writing good Lewis structures. The first thing we do is sum the valence electrons from all atoms. We do this by looking at the periodic table and determining how many valence electrons each atom has and total up all of the valence electrons. If there is a negative charge, we add electrons. If there's a positive charge, we subtract an electron from the total number of valence electrons. Next, we use a pair of electrons to form a bond between each pair of bound atoms, and we subtract however many electrons we need to form at least a single bond between atoms. Keep in mind that atoms usually have noble gas configurations, so we look at how many electrons we have remaining and we distribute them so as to satisfy as many octets as possible. Remember, for hydrogen, we only need a duet of electrons. If we cannot satisfy all of the octets, then we start moving electrons around and try making double or triple bonds to satisfy all of our octets. For water, we would sum the total number of valence electrons at 8. Two times 1 electron for each hydrogen, plus 6 electrons for oxygen to give us 8 electrons total. We need at least a pair of electrons between each hydrogen and oxygen. Hydrogen can only have a duet of electrons, so we have now satisfied the duet on hydrogen. We've used 4 electrons, which gives us 4 electrons remaining. We'll distribute those as pairs on oxygen. Now we have all of our electrons used up. We have an octet of electrons on oxygen and duets on hydrogen. We've come up with a good Lewis structure. There are plenty of examples of writing Lewis structures that can be followed. Notice that for hydrogen, we're always going to have a duet. Our halogens will typically only make single bonds because they only need one more electron to have an octet. Carbon forms 4 total bonds. This can be 4 single bonds or some number of double and single or triple and single bonds. So now let's examine some exceptions to the octet rule. If we look at boron, boron tends to form compounds in which the boron atom has fewer than 8 electrons around it. It oftentimes does not have a complete octet. It only has 6 electrons surrounding it. Boron likes to be electron deficient. It's an excellent Lewis acid. If we look at BH3, where we have 3 valence electrons for boron and 3 times 1 valence electron for hydrogen to give a total of 6 valence electrons. Once we've made single bonds between boron and each hydrogen, we have no more electrons. BH3 will have an electron deficient boron. BF3 will be very similar. There will be octets around all of the fluorines, but only 6 electrons around the central boron. Aluminum will behave similarly to boron. In fact, boron is, as I said, an excellent Lewis acid. Because of its electron deficiency, it will coordinate with lone pair electrons to form a boronate, a negatively charged boron. Here we have an amine borane. There are also exceptions to the octet rule where we see more than 8 electrons around a central atom. When it's necessary to exceed the octet rule for one of the elements present, elements in the 3rd period or lower on the periodic table can have expanded octets. We will place the extra electrons on these central atoms, such as sulfur or astatine. Here, sulfur has 10 electrons around it, as does astatine. As seen in sulfur hexafluoride, sulfur can have up to 12 electrons in its expanded octet because of the availability of d orbitals to expand electron octets and expand electron pairs into. Phosphorus is another element which we commonly see have more than 8 electrons around it. Here in phosphorus pentachloride, the central phosphorus, represented in yellow, has 10 electrons surrounding it. So let's review. Carbon, nitrogen, oxygen, and fluorine should always be assumed to obey the octet rule. Boron and beryllium often have fewer than 8 electrons around them in their compounds. Second row elements never exceed the octet rule. Third row and heavier elements often satisfy the octet rule, but can exceed the octet rule by using their empty valence d orbitals. When writing Lewis structures for a molecule, satisfy the octet rule for the atoms first. If electrons remain after the octet rule has been satisfied, then place them on the elements having available d orbitals, elements in period 3 or lower.